Sir, welcome, Professor.
Yeah, good morning, sir. Good morning.
Sir, good morning, sir. Good morning. Sir, DK Singh, sir. Hello.
Good morning, sir. Good
Good morning, sir.
morning.
Good morning, sir. Very warm welcome, sir. Thank you, sir.
Thank you.
Sir, we can start, sir.
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
So, a very good morning to Dr. D.K. Singh. Welcome, sir. Professor D.K. Singh.
Yes, sir.
Yeah, hearty welcome to you, sir.
Thank you, sir.
Thanks for agreeing our request to deliver invited talk in this international conference. I now invite Dr. Balamuralidharan to introduce the speaker.
Yes, sir. Yes, sir.
Yeah.
Sir, is it audible, sir? Audible, sir?
Yes, sir. Yes, sir.
Okay. Dr. D.K. Singh, working as assistant professor in the Department of Mathematics, School of Basic Sciences, CSJM University, Kanpur. His PhD degrees in fractional calculus. He edited a book entitled The Fundamentals of the Fractional Calculus for Taylor and Francis Journal. He has published 19 research papers and 4 book chapters. He is the editor of another accepted book proposal entitled Recent Developments in Theory and Applications of Fractional Order Systems for Elsevier. He has received an award from the Society of Special Functions and Their Applications for the best publication in 2019. He has completed the C.V. Raman project. His research interests lie in fractional calculus, special function, partial fractional differential equations, and distribution theory. Apart from being a reviewer in esteemed journals, he is participating in many national and international workshops and conferences, and a life member of Vijayan Bharati, the Society of Special Functions and Their Applications. Sir, welcome. Sir, very warm welcome to you, in our new reign, sir. Sir, please take over this session, sir. D.K. Singh, sir.
Okay, sir. Thank you.
Thank you, sir.
Thank you and good morning, all. Is this visible, sir?
Yes, yes, sir.
The PPT is visible, sir?
Yes, sir. Visible.
Yes, sir. Yes, sir.
So, thank you, sir, and good morning, all. Now, today's invited talk will be introduced to a new form of fractional calculus, as incomplete fractional calculus. So, before knowing incomplete fractional calculus, will be know what is a fractional calculus. So, besides a generalization, the notation of a factorials, the gamma function can be used in a variety of a situation to generalize discrete process into the continuum. Such generalizations are not new. However, mathematicians over the year have concerned themselves with this concept In particular, the question concerning derivative of non-integral order was first raised by the Leibniz in 1695. Many years before, Euler introduced the gamma function. So, however, the concept of function, we can write this derivative formula gamma a plus 1 divided by gamma a minus mu plus 1 x over a minus mu, where gamma is greater than or equal 0 here, where 0 is not restricted to integer value. So, equation provides a simple method of computing fractional order derivative of the polynomials. So, I'm giving us some one examples here. So, if you write here mu is equal to 1 by 2 and a is equal to 2 here, and you express and if you have the express this derivative in the here gamma here, so you will get here gamma 3 divided by gamma 5 by 2 x over 3 by 2 here. So this form is known as the what here? Fractional derivative here. This is the fractional derivative here. So after that, so why is the fractional calculus called incomplete fractional calculus? So these two functions are responsible for an incomplete word. So first function is the incomplete gamma function. Another function is the complementary incomplete gamma function, and we are aware about these two functions. So incomplete gamma functions can be represented here. This is the gamma s x here. 0 to x, so we should concentrate about this limit of integration 0 to x here. Base e over minus t over s minus 1, dt where s is the greater than 0. And this is the complementary incomplete gamma function. And this is here complementary gamma function here. So we should be concentrate about this notations here. This small gamma, this is called the capital gamma here. So gamma sx here, x to infinity, t here, limit of integration goes to x to infinity, base over minus t, ts over minus 1, dt where s is greater than 0. And these two incomplete gamma function, the complementary incomplete gamma function, follow the decomposition rules here. So if we follow decomposition rules, so we can obtain here gamma formula, gamma function here form. So these two are a very important function which are playing a very important role to introduce incomplete fractional calculus here. So now we are coming at the here incomplete Cochammer symbol. So what is the incomplete Cochammer symbol? So incomplete Cochammer symbol constructed with the help of these two functions, incomplete gamma function and complementary incomplete gamma function here. So if you look here, this is the here incomplete Cochammer symbol here form. So this is a two different notation. First notations represent what here? Incomplete gamma function here form, and second notation is represent what here? Complementary gamma function. So that's we can say that incomplete Cochammer symbol can be constructed with the help of the incomplete gamma function and the complementary incomplete gamma function here. So these incomplete Cochammer symbols, this is the here these two equation 3 and 4 satisfy the following decomposition formula. So if you write here these incomplete Cochammer symbol in this form here, if you add these two here, so you will reach here at the here that is the Cochammer symbol here form here. So this is the conditions here, lambda mu belongs here C and x should be greater than or equal 0. This is also giving the here convergence condition in form, that is the here mod of here lambda x mu here should be less than what here Cochammer symbol mu here. So these two incomplete Cochammer symbol must be less than or equal, this is the here Cochammer symbol here. And this will provide that the defining the infinites in the case is the absolutely convergent here form here. So now the class of the fractional calculus. So now here incomplete hypergeometric function. Now we'll be discuss about the incomplete hypergeometric function. Then we'll discuss about the here operators of the incomplete fractional calculus here, because without incomplete hypergeometric function, we cannot introduce the incomplete fractional calculus, because these two are the playing very important role to represent the incomplete fractional calculus operators here. So these two formulas, incomplete hypergeometric function, construct with the help of the here incomplete Cochammer symbol. These two are here. This is the here incomplete Cochammer symbol form. This is the incomplete Cochammer symbol here form, and we know that here incomplete Cochammer symbol construct with the help of the incomplete gamma function and the complementary incomplete gamma function here. So if you look the notation of the hypergeometric function, incomplete hypergeometric function form, so this is the P here and this is the Q here. P is the represent what here? Numerator here, and Q is the represent what here? Denominator here. So these are represented here numerator form, these are represented here numerator form, and these are represent what here? Denominator form, these are represent here denominator here form. So we can write here this hypergeometric function form in a summation form like that. One here, this is the incomplete Pochammer symbol, this is the A2 Pochammer symbol, AP Pochammer symbol, B1 Pochammer symbol, B2 Pochammer symbol, and B2 Pochammer symbol is Z over K here, the factorial K here form. So again, this look here, this notation, these two notation, this notation for the what here are incomplete gamma function, and this notation is represent what here? Complementary incomplete gamma function here. So with the help of the incomplete Pochammer symbol, we are representing here the incomplete hypergeometric function. Again, if we apply here decomposition form for the 7 and 8, so we can arrive at a classical hypergeometric function here form. So hypergeometric function form nothing but this is the generalization of the geometric function which is given by the Gauss here. So with the help of the decomposition form, we can obtain the here classical hypergeometric function here form. So what is the incomplete fractional order integrals and the derivative here? So the class of the fractional operator equation of various types play very important role not only in mathematics but also in a physics, control system, dynamical system, and the engineering. Fractional differential equation has been of interest of many researchers in recent years, and there are many authoritative accounts of the fractional calculus and fractional differential equations here. Over the years, many mathematicians using their own notation approach have found various definitions that fit the ideas of a non-integer order integral or a derivative here. So in this talk, our aim to introduce fractional calculus as a new tool using incomplete hypergeometric function here. So these formulas earlier introduced by these operators are introduced by the Segal 1978 with the help of the hypergeometric function. Now I am introducing these fractional order integrals and derivative in the form of the here incomplete hypergeometric function here. So that's why we call this is the here incomplete fractional order integrals and the derivative here. So this is the here notation of a fractional integral. So this is the represent what limit of the integration, because this is the 0 to x here, this is a 0 to x here, and this limit of integration also used in a incomplete gamma function here. So we write here this notation in a form of here x over minus alpha minus beta divided by gamma alpha x minus t alpha minus 1, and this is the here incomplete hypergeometric function. This is the here function of ft dt where here alpha is the greater than 0. So this integral can be also represented in a derivative form, and a derivative form dn of dxn here. We can write here this integral in a form of here. This is the here notation of the here complementary gamma function here form 0 to this is the x here, and you can write here alpha plus n, beta minus n, gamma minus n f here function of x here, and this is the here condition for a real alpha plus n should be greater than 0 and less than or equal n, where n is the greater than n is belonging and not here. This is the here form. So we can say that here this is the incomplete fractional order integrals and derivative construct with the help of the here incomplete gamma function and complementary incomplete gamma function here. So that's why I'm just showing to here limit of the integration here 0 to x here, and I'm showing to here this is the here this is our incomplete hypergeometric function here. So with the help of the incomplete hypergeometric function, we introduce the here incomplete fractional order integrals and the derivative here. So again, because we have the two limit of the integrations here, because we have the two limit of integration 0 to x, so we are using the I 0 plus and another limit of integration x to infinity. That's why we are using the notation I minus here. So this is the here, because we are using the here limit of integration 0 to x, so that's why using the 0 plus here, and because we are using the limit of integration x to infinity, so we are using the here minus notations here. So this is the here incomplete fractional integral here form. So these fractional integrals form are here 1 by gamma alpha x to infinity t minus x over alpha minus 1 t over minus alpha minus beta. Again, this is the represent what here incomplete hypergeometric function of ft dt here. So this integrals can be represented in a form of what here and a derivative here form. with this notations here, dn of dxn here, I, this is the here, complementary gamma function, this is the alpha plus n, beta minus n, gamma here, and this minus notation is the represent limit of integration x to infinity, function of x here, and this is the conversion, this is the conditions for here, real alpha plus n is greater than 0 and less than or equal 1 here, where n belongs here, n not here. And we can represent here, this is the here, incomplete derivative form here, fractional derivative here form, and this will represent what here, incomplete fractional integral here. So this the incomplete fractional derivative can be represented in a form of here, incomplete fractional integral here with this notations here. So this is the incomplete fractional derivative. If you represent here this notation, this is the notation here, this is notation here, this is the here incomplete fractional derivative notations. If you represent here this form, at the place of alpha you are representing the minus alpha, at the place of beta you are representing the minus beta, and at the place of gamma you are representing the alpha plus gamma here. So you can easily represent your fractional in fractional derivative in a form of incomplete fractional integrals here. So also you can represent this because I have already told you, this is the here incomplete fractional integral can be represented in the form of here incomplete, this is the here antiderivative of the incomplete fractional integral here. So I'm trying to here write the here this incomplete fractional integral in a form of antiderivative of an incomplete fractional integral earlier. So now, so this is the condition here, real alpha is greater than 0 and n is equal to real alpha plus 1 here. After that, this is another here form because I have already discussed earlier here. If you are there are a two notation here form, again just I'm saying that here 0 to x limit of integration x to infinity. So that's why using the here two notation form here, plus and minus here for the integrals and the derivative here. So again, this is the here form, plus here for the 0 to x here, and this is a negative here for x to infinity here. So again, we are using the here because we have already discussed here, if you have the limit of integration from here 0 to x here, and so will be limit of integration here x to infinity here. So that's why we're using the here negative sign here, d minus here alpha beta gamma function of x here. So this derivative also can be represented in the form of the fractional integrals, incomplete fractional integrals here. So we have the fractional integrals formula is the here gamma here, this is a minus here, minus alpha minus beta alpha plus gamma f here function of x here. So this is the here fractional integral, fractional incomplete integrals can be also represented in the incomplete derivative here form and a derivative form. So we have the notation, this is notations here, minus 1 over n dx over n, gamma here I minus alpha plus n minus beta minus alpha plus gamma f here, x here, where the condition real alpha is greater than 0 and is equal to what here, real alpha plus 1 here. So now, so there are some tools here. So that's why if here, so we'll be introduced here, or we can, so I'll just show you that how we are proof here this operator from where we obtain this operator here, these from where we obtain these operators here. So that's why I'm using the here some theorem here. So if here alpha beta gamma belongs C here and let here x is belong here reals and incomplete fractional derivative of the function f x belong here real for the relations. So this formula here I have already shown in a previous slide. We can represent our incomplete fractional integrals can be represented in a here derivative forms here. So that's why I am representing this incomplete fractional integral in a derivative here form. So or we can say that here that's integration is the inverse process of the differentiations. We can use this process here to calculate the formula. So we are using the here derivative here form. So I'm choosing the here right hand side to prove these theorems here. So dx can be represented here 0 to x here alpha plus 1 beta minus 1 gamma minus 1 f x here. So if you're representing this incomplete fractional derivative in this form here x over minus alpha beta gamma here alpha plus 1 0 to x x minus t alpha minus 1 to the gamma 1 here, and this is represent what incomplete hypergeometric function of ft and the dt here. So now if you are representing this incomplete hypergeometric function form in a summation form, so if you're representing in a summation form and you are using this formula, now with this formula representing here, where n is equal to what here, x over gamma minus 1 minus x over alpha plus beta minus gamma. So we can express this expression, this derivative expression. So this derivative expression can be represented here, d of dz, z here gamma minus 1 minus z alpha minus gamma plus 1, to gamma 1 here, alpha x here, beta gamma z here. And if you're writing here this z here at the place of this is what here, x minus t. So you will get here the derivative of these d dx of here x minus t 2 gamma 1 alpha plus beta x minus gamma plus 1 alpha plus 1 here 1 minus t x here. And if you are using this formula, for this integral here, so you will get here this form of the incomplete fractional integrals here. So this is the here. So we have the here another theorem here, because already just say you that we have always here 0 to x and x to infinity. For the 0 to x we are using the positive sign, and for the x to infinity we are using the negative sign. So that's why again we are using the negative sign. So we have the here form alpha beta gamma belong C here, and let here x belong R here, the incomplete fractional derivative of the function fx on here R plus hold the relation. So we have the here. So again this is the here incomplete fractional integrals here. So we can write here, and again in the here derivative form minus 1 here d of dx here, gamma minus here alpha plus 1 beta minus 1 gamma fx here. So again for the proof here we are using the here right hand side of the equation 15 here. So equation 15 right hand side can be expressed here from d of dx here 1 by gamma alpha plus 1. So we are using here this formula. We are using here this formula to represent here. We are using here this formula to represent here I0, I here minus here alpha plus 1 beta minus 1 gamma function of fx here. So we are using here the this integral representation here to construct our equation 15 here. So if you write here 1 by here gamma alpha plus 1 x to infinity t minus x over alpha, t over minus alpha minus beta 2 gamma 1 alpha plus beta x here minus gamma alpha plus 1 minus x by t function of ft. So again using the differentiation formula for above expressions here, d and a derivative formula of a d and dz in here, zc minus 1 2 gamma 1 ax here b c z can be represented here. This is a Pochamer symbol here form c minus 1 over n, z over c minus n minus 1 2 gamma 1 ax here b here c this is the incomplete here Pochamer symbol, b here semicolon, c minus n here semicolon, z here. So if you differentiate here this expression up to n derivative, so you will get here this expression which including the here Pochamer symbol and the incomplete hypergeometric function here form, and using this formula for this integral here, so you will get your equation 15 here. So we can use the here, or somebody's thought like that how these are happening here. So we just remembering here integration is the inverse process of the differentiation. So you are using here this process here to calculate the formula 15 and 15 here. So now we have the another theorem here. So this is what is the another theorem here? If alpha beta gamma is belong C here and let x is the belong R here, so then incomplete fractional derivative in theorem 1 and 2 we already discussed about the incomplete fractional integrals here. So now we are discussing about the incomplete fractional derivative of the function of fxr, which are hold the relation here. This is the here complementary gamma function here form d here 0 to x alpha beta gamma f here function of x here. So this can be represented here the nth derivative of the integrals here, nth derivatives of the incomplete fractional integrals here. So if you write the here, this is the here form, so you will get here or you can write here this nth derivative of the incomplete fractional derivative in a form of here I here 0 to x minus alpha minus beta alpha plus gamma f here. This is a x here. So it is similar to the previous theorem 1 here. So similarly we can prove here as a theorem 1. So this is here. So now we have the another theorem for the incomplete fractional derivative here. So in this theorem third, we are discussing about the here 0 to x. That's means we are discussing about the d here plus here. Now we are discussing about the minus here. So we are using the limit of integration x to infinity here. So here alpha, beta, gamma belongs x here, and let x belong r. The incomplete fractional derivative of the function fx on r holds the relation here d here. This is the alpha, beta, gamma f here function of x minus d of. So this incomplete fractional derivative can represent the nth derivative of the incomplete fractional integrals here. So this is the nth derivative d of dx of n can be represented here. This is the complementary incomplete gamma function minus here limit of integration goes to what here x to infinity, and this is form minus alpha n minus beta minus n alpha plus gamma f here. Or you can represent here this nth derivative of the fractional integral derivative in a form of here. There's the incomplete complementary incomplete gamma function. There's the minus here minus alpha minus beta alpha plus gamma f of x. So similarly we can so it is similar to previous theorem 2 here. So which method we are using here to get the result of the theorem 2 here. So we can use these method to calculate the theorem 2 here. So now in a theorem 5, this is the here we know that the here fractional operators equation are very types play very important role. We have already told you, not only in mathematics but also in physics, control system, dynamical system, and engineering here. So we are discussing about the here fractional integrals operators here. So this is here theorem here alpha, beta, gamma rho belongs here. Where alpha is greater than 0, real rho is the greater than maximum 0 real here. Beta minus gamma and condition 6 is just here. So what is the condition 6 are here? So condition 6 that's mean here that is the convergence condition of the incomplete Kochamer symbol. This is the convergence condition of the incomplete Kochamer symbol. This is the conditions here. This is the conditions here. These conditions should exist here for the any incomplete form here. So that's why I'm using the here. If these condition 6 exist here, so then we can obtain the here fractional integrals incomplete fractional integral operator here. So this incomplete fractional integral operator is the form of the here gamma rho, gamma here rho plus gamma minus beta divided by gamma rho minus beta, gamma alpha plus rho plus gamma x over rho minus beta, and this is minus x over alpha plus rho minus 1 and gamma alpha plus beta plus 1, gamma rho alpha plus rho to f1. This is the hypergeometric function. This is represent numerator and this is represent what here denominator here form here. In the what is the difference between my formula and the Sego formula? So in a Sego formula, you cannot get here this part here. You cannot get this part here. Only Sego is given here only this part here. Only given this part here. So that's why in an incomplete fractional calculus, you can get here this part also here, and this is a playing very important role in a dynamical system, control system, physics and engineering also here, or you can get here more generalized form of the any functions here. So now here, so how do you get here this equation number 19 here? So we have the here with the help of the 6 and 7 here. So with the help of the 6 and 7, with the help of 6 and 7, this is the here form. So we write the here this here I0 x alpha beta gamma t over rho minus 1 x can be represented here. This formula k is equal to 0 to infinity using the here same formula equation like here 7 here, this equation like 7 here. If you write the equation like here 7 here, this is a equation form here. Sorry, this is the equation number here like here 9 here. Sorry, this is the equation number like here 9 here. We are using here this form to represent here I0 x alpha beta gamma f function of x here. So that's why we are using here this form here to represent here fractional integrals derivative form. So we are using here this form here 0 x alpha beta gamma t over rho minus 1. So we are expressing this incomplete fractional integral derivative in incomplete fractional integrals in the form of your summation k is equal to 0 to infinity. This is your incomplete Kochamer symbol here form minus gamma. This is your Kochamer symbol here form. This is also the Kochamer symbol of alpha and factorial k, and using the here 0 to x minus t alpha minus 1 minus t by x over k t over rho minus 1 dt here. And we are using the here if you substitute here t by x is equal to u here, so you can represent here this integral in a form of the beta function here form. So we are using the here beta function form. So after using the beta function form, its whole expression change in here incomplete hypergeometric function form. In this whole expression change in incomplete hypergeometric form. So we are known about the what is the formula for this incomplete hypergeometric form here. So this is the formula 2 gamma 1 A. This is the incomplete Pochamer symbol here, incomplete Pochamer symbol. B here C and 1 here. So we can represent this incomplete hypergeometric function form if you get the here at the place of x or z equal to 1 here. So you will get here this form gamma c minus a minus b divided by gamma c minus a gamma c minus b minus x over a divided by gamma a plus 1 2f to c minus b a c a plus 1 here minus x here. So if you are using here this formula here in equation 20 here, so you will be get here. So you will get here this form here. So you will be get here your this result here, this result, equation number 19. So if you are, it is very simple here, just using the incomplete fractional integral formula here and write the hypergeometric function in a summation form here and represent this integral in a beta function form here and using here this formula to here. So you will get here your equation number 19 here. So now again we have the here some so now we have the here some special cases for this formula here. This is this formula here. So how will we get the special cases here? So again we have the formula 1 upon gamma a 0 to x t over a minus 1 1 f1 c minus b c n minus t. So you can represent here x over a. This is the here integral formula for the hypergeometric function here. X over a divided by gamma a plus 1 2f2 minus c minus b a here c here a plus a minus x here. So if you represent here this integral formula, so this is 17, equation number 17. This equation number 17 becomes here. So equation number here 17 becomes here this here form. So this is the here form. That should be not equation number 17. That should be your equation number. This is about here 19. 19 should be becomes here this here form I0 x here alpha beta gamma to the rho minus 1 x here. So we can represent here this integral in this form here, and if you are using the here, if you are using the here, look here, this is a gamma alpha plus beta plus 1 divided by x over alpha plus beta 1 upon gamma alpha plus beta, and if you are using the here, this form here, alpha plus beta, gamma alpha plus beta, using the gamma formula here. So if you are using the gamma formula, so this gamma alpha plus beta and gamma alpha plus beta will be cancelled out here. You have only alpha plus beta divided by x over alpha plus beta 0 to x t over alpha plus beta minus 1. This is the here represent what here? Confluent hypergeometric function. This is a dt here. So this equation number 23 is playing the very important role for the special cases here. So now if you choose the here case 1 here, if you put the here beta is equal to minus alpha in equation number 23, in here 23 here, so we will get here, I think this is here some typing mistakes here. I think it's so if you substitute here beta is equal to minus alpha in equation number 23, then equation 23 becomes as the Riemann-Liouville fractional calculus operators here. So this is the here. So equation number 23 becomes the here Riemann-Liouville fractional calculus operators here, which is the classical formula of the fractional calculus here. So you can represent here, look on the here, if you put the beta is equal to minus alpha, so this part becomes 0 here, and you will be get here only this part here. This is the this part becomes 0 here, and you will be get here only this part here. Gamma rho, gamma here rho plus gamma minus beta, gamma here rho minus beta, gamma alpha plus rho plus gamma x over rho minus beta minus 1 minus x over alpha plus rho minus 1 divided gamma alpha plus rho plus beta plus 1 gamma rho alpha plus rho 1 here. So if you put the here beta is equal to minus alpha, so you will be get here, and if you calculating here this expression, so you will be get here this is here Riemann-Liouville fractional calculus operator in a form gamma rho divided by gamma rho plus alpha x over rho plus alpha minus 1 rho is the greater than 0 here. So similarly, if you put the here beta is equal to 0 in this here expression, here, so you will get here delay operators here. This in the if you substitute your beta is equal to 0 in this equation 23 here, so you will be get here this form again here. So beta is equal to 0, so you will be get here this form gamma rho plus here gamma here alpha plus rho plus gamma x over rho minus 1, and you will be get here this expression with the help of with the hypergeometric function here form. And if you calculating here these expressions, you will get here this is the here this expression here with the here incomplete hypergeometric function form, and this is a represent what here ideally polar operator here form, which is the classical formula of the fractional calculus here. So this is but I'm representing this classical ideally coded operator in the form of the incomplete fractional calculus here form. So by using the same technique we have the here because we are using the here complementary gamma function here, and now we are using here incomplete gamma function here. So this is here, so gamma here 0 to x here. So if you put the beta is equal to 0, so you will get here these notations here for the ideally coded operators here. So if you add in equation 25 and 26 here by using the decomposition formulas, you will get the classical ideally coded operator here. So now for a theorem 6 here, so again, if you are using the here, because this is another fractional integral operator here, so we are using the here same technique. So if alpha, beta, gamma here rho is belongs here, alpha is greater than 0, and this is the here convergence for the real rho here, maximum here real minus beta and real alpha minus gamma here. So we have the then we have the here fractional integral operator form like this one here. So how will you prove here this theorem here? So this is again we are using the same technique to prove the here these linear fractional incomplete fractional integral operator here. So we are using the here integral form of this incomplete fractional operators here. So we are using the this integral form here, and we are writing the incomplete hypergeometric function in a summation form, and we are using the here x by t is equal to u here, and we are transfer here this integral in a form of the beta function, and we are using the beta function here form, and we are calculating this expression. So we are obtaining the here incomplete hypergeometric function form, and we are using the again the incomplete hypergeometric function formula. This formula here, if you are using the again incomplete hypergeometric formula, this one here, so we can easily obtain the here this operator equation number 27 here. So now we are here are some special cases here. So if you take the beta is equal to minus alpha in a 27 here, if you take the beta is equal to minus alpha in 27 here, so then we have the here value operator here. Value operator is nothing but this is a classical fractional calculus formula here. So we can represent this here beta is equal to minus alpha. If you represent the beta is equal to minus alpha, so we are getting the here value operators here, and this is the here conditions for the real alpha is greater than 0 and real 1 minus rho is here less than minus real alpha here. So again we have the here set beta is equal to 0 here in this equation. If you substitute here beta is equal to 0 here, so again will we get the here ideally coded operator here. This is represent the here incomplete ideally coded operator here in the form of the here x to 0, x to infinity here, and by using the decomposition formula in equation number 13 and 31, we can get the here classical ideally coded operator here. So now we have the number of the application of this incomplete fractional calculus. First application with the right function here. If you are this is the right function, nothing but this is the form of the this is the form of the hypergeometric function here form. This is the generalization hypergeometric function form. And if you are using the here at the place of ft, we have the here this formula. If you look here any formula here, if you look here at the place of t minus rho or the place of the ft here, we are using the here. We are using the here. This is the here right function here form, and we are calculating it here at the previous method, theorem 1, theorem 2, theorem 3, theorem 4, like here. So you will get here this result here. So you will get here this result here. This result represents the more generalization form of the right function here. More generalized form of the right function here. So in a theorem, so next form is the Meta-Glaffer. Next application with the Meta-Glaffer function here. Meta-Glaffer function is nothing but this is the here generalization of the exponential function. If you substitute here alpha is equal to 1, so you will get your exponential function. So this is the here one parameter, and this is the with the two parameter here, and this is known as the generalized Meta-Glaffer function. If you substitute alpha is equal to 1, beta is equal to 1, so you will be get here exponential function here form, and this is the here more generalized form of the this Meta-Glaffer function here, which is given by the Prabhakar here. He is using the another parameter gamma here. So if you represent this Meta-Glaffer function in your form n is equal to 0 to infinity, this is the Pochammer symbol gamma alpha k here beta 0 over n here factorial. If you substitute gamma is equal to 1, this will be converted in a factorial form, and factorial will be cancelled out here. Alpha is equal to 1, beta is equal to 1, z is equal to Z over n. So if you substitute alpha is equal to 1, beta is equal to 1, gamma is equal to 1 here, so again will be arrived at the exponential form because Metcalfe function is the generalization of the factorial function. So with the if you are using the here Metcalfe function here form here, so again using the same process like a theorem 1, theorem 2, theorem 3, whatever we are using the method to solve the theorems here. So again we are using the same process to calculate here this theorem, so we can easily get our result here 39 here. So this is the here, so I'm just showing you here how you're using the here. So write the here this formula integral form here, and you write the here this Metcalfe function in summation form using the beta function formula. So if you after using the beta function formula, you will get here this result. And if you are using the fractional integral operator, so you can easily obtain the equation number 39 here. So again, next application with the h bar function here. So there's the h bar function. So this is the h bar function is the here one application name is the inheritance in terms of Milan-Barnas contour integral here. So if you are associate our incomplete fractional formula with the help of this h functions here, so we are obtaining here this result here like this one here. So this is the result here. If you are associate our here incomplete fractional integral formula with the h bar function here, so we obtained here this result here. This is similar to the previous theorem like 7 and 8. It is similar to the previous theorem 8 and 7 and 8 here. So now another application with the Bessel function here. So we are everyone is well known about the Bessel function here. So with the Bessel function, if Bessel function associate with the here our incomplete fractional integrals or derivatives here, so we obtain here this result here form. So look here, this is the represent what here right function. This is the represent what here right function. All these result in represent what here right function here form. If you look here, this result are represent what here right for your function form here right function here form. So this is the right function here form. So all these result in a right function here form. So we can say that here that's an incomplete fractional calculus is a represent if these associate these functions, so it is represent in a right function form. Right function nothing but this is the form of the what here or a hypergeometric function here form. So now this is the Milan transform of the incomplete fractional calculus. The Milan transform of the function fx denote here by f bar s. This is the formula of the Milan transform. If everyone is aware about the Milan transform, so Milan transform is also associated with the incomplete fractional calculus operator here. So if you are using the Milan transform of the fractional incomplete fractional integrals here, so we are getting here this form of the here, which is the represent here in the form of the generalized hypergeometric function. This is the form of the Milan transform here. So these are the references. And what is the conclusion of these things here? So I will just tell you here the importance of this incomplete fractional calculus lies in fact that nearly all the special functions appearing in applied mathematics and study of the incomplete fractional calculus operator will cover wide range of the integral equation, differential equation, and it will give deeper, more general, and more useful result in various problems, science engineering, some differential properties, integral representation, and special cases are here. So now this is the references which I am using here to write the incomplete fractional calculus here. This is the references here. This is the references here. So thank you.
Professor, very nice presentation. Professor, very nice presentation, Professor.
Thank you, sir. Thank you. Thank you very much.
Okay, thank you. Sir, any questions from the audience? Hello, any questions from audience?
Hi, sir. Good morning. Hello.
Good
Yes,
morning.
sir.
Good morning.
Yes, sir. Yes, sir.
Yeah. This is Prakash Pandey from University of Mumbai, sir.
Yeah, you can.
First of all, I will congratulate this team, and I will also congratulate Dr. D.K. Singh, sir. So it was a very nice presentation, and you explained very well, sir. You know the topic called as fractional calculus and incomplete fractional calculus. Sir, actually, I am doing research on this topic called as fractional calculus and basic hypergeometry series.
Oh, nice.
Yes, sir. So I am doing the extension part. I am working on fractional Q calculus.
Oh, fractional key
So,
calculus. Okay.
yes, sir. So my question is that, sir, can I relate this fractional Q calculus with incomplete gamma function? Because
Of course, you can relate with the key calculus here. Still, I'm working with the key calculus. I'm also trying to represent our incomplete fractional calculus in a Q incomplete fractional calculus here form. But still, I'm working. Okay. So when I get the some result, so definitely I'll share with you.
yeah, because when I saw your this presentation, sir, na, so it came in my mind means
Yeah,
such a
definitely you can.
interesting and
Definitely you
wonderful
can.
topic is
Yeah,
incomplete.
yeah, yeah. You can. This is a very good job.
Thank you,
Yeah.
sir. Thanks a
Yeah,
lot.
you can.
Thank you, sir.
Yeah, you're welcome.
Okay, any other questions from audience? Hello, any other questions?
So thank you, Professor D.K. Singh, for the excellent presentation.
Thank you, sir. Thank you very much. And thank you
Thank
for
you very much
inviting
for,
me.
yeah, thank you. Thank you for gracing our conference by your participation and delivering an excellent talk, sir. Thank you, sir.
Thank you. Thank you very much, sir.
Sir, computer science, madam joined, sir. Chairperson, madam joined, sir.
Very good, sir.
Yes,
We
sir.
welcome the chairperson of
Lakshmi
the
Prabha.
session for
Lakshmi
computer
Prabha.
science.
Yes, madam.
Sir,
Lakshmi Prabha, madam.
sir, can I leave?
Dr. Lakshmi Prabha. Yes, sir. We welcome. Thank you, Professor D.K. Singh. All the participants kindly be in track 1 for the. So our next program is.
Sir, yeah, just now we started Innoted Talk, sir. Sir,
Yes, sir.
presentation, oral presentation.
Yeah,
Oral presentation, 10:30.
Yeah, we start with the oral presentation.
Yes, the mathematics track 2, sir. Mathematics track 2.
Yeah, all track 2 delegates kindly move to track 2 for oral presentation. In this track 1, oral presentation will start under the chairmanship of Dr. Lakshmi Prabha Somasundaram. Welcome, madam. Welcome. Madam, your mic is off, I think.
Am I clear now, sir? Am I audible?
Yes, madam.
Yes,
Yes,
madam.
sir.
Yes, madam.
Good morning.
Thanks
And
for
I am very
joining.
happy to be part of the RAINS group. And
okay, thank you, madam. Thank you, madam.
yes, sir. Yes, sir. Personally,
Thank you.
Bala Murali.
Yes, sir.
Yes.
Thank you, madam.
Thank you, sir.
Thank you, madam. Thank you. So let us start
Yes.
the oral session, madam.
Yes, sir. I'm ready.
Yes. Yeah. Delegates, kindly type your abstract number and name so that it will be easy for us to call you. Balaji, are you available?
Yes, sir.
Yeah. Who is the first participant, Balaji? I think today it starts with 41, right?
Yes, sir.
Abstract number 41 is available. Participants, kindly type your or text your abstract number so that it will be easy for us to identify whether you are available.
56
Okay,
available.
shall we start with 56, Ms. Anisha Asirvadam.
Good morning, sir. Good morning, ma'am. Shall I present, sir?
Yeah, please. Share your PPT
Yes, sir.
and start your presentation.